Whoever knows calculus has a significant advantage because sometimes you don't need to analyze data. Sometimes when you see the data plotted, you say, oh, this plot looks like a model or a function I know very well. It allows you to analyze oscillations. It allows you to concentrate in interesting points. Sometimes it's not necessary to study the whole range of values of a variable, so only concentrated on one point. And that brought the concept of Taylor series, for example, when you're just focusing in a single point. I don't expect you to become mathematicians in one session. That will not happen. Of course, mathematicians know more than this, but let's say they have been studying years and years the many concepts. But at least you will know that these tools exist and that you can use it. Then the first part of this class, I will just introduce basic concepts of calculus. I already mentioned the motivation. One of the motivations was that the other motivation of calculus is analyze variations, how a variable change with respect to the other. For example, you have data, you can plot the data, X, Y, or whatever letter you want to put, and you want to understand what is the change, the rate of change from one point to the next, or you want to know the slope, instantaneous slope. You know why it's a slope, no? A slope. The inclination of the curve, or the inclination when you have a straight line, the higher the inclination like this, the higher the slope. Like when you are seeing the racing cars in United States, particularly, is some circular racing circuit, and there is some slope, no? So we call it a slope, the inclination. It's a measure of inclination. Later, I will correct the attendance to those who attend, just arrived. You arrived after I call, right? Did Priscilla tell you something about your research, or did you talk to her? Yeah. Okay, right. No problem. I am not a morning person either. Don't worry. Then let's start. We have we will see two parts of calculus, differential and integral. There is calculus in 3 dimensions also, but I will not touch that because it's just an extension, and some of you might use, some of you might not use. Calculus start from the concept of limits, but I will not introduce the limits because it will be too much for you. But look at this, for example, we have y and x here, and you have this curve here. If I calculate, you know what is the derivative of a function? Derivative of a function, derivative. Okay, derivative. I will write here. More. Let's assume I have two variables like that, y and x. The derivative of y with respect to x. We call this derivative. And there are some rules for evaluating. What does it measure? If I calculate the derivative here, in this point, for example, I calculate the derivative of this function, dy dx, and I evaluate that at this point, which is x equal 2. It gives me the slope of the tangent line to this point, the slope. So I can know the equation of this straight line. What is the equation of a straight line? Somebody can tell me? Straight line, slope, x plus a curve. This is a straight line. So the derivative of y with respect to x of a straight line is just m. The slope. So in other words, that's why the derivative measures the slope at a single point. in these cases. Okay, those concepts will be clear probably later. We have differential calculus, we have integral calculus. Integral calculus helps us to calculate, it's the opposite operation to derivative. For example, in some cases, it helps us to calculate the area below some curves. In some cases, for example, in the case of economy, helps us to calculate the revenue of an organization. Revenue, because the revenue is a plot and you have to calculate the area below the curve. And that area represents the revenue or the number of sellings or whatever. Okay? Money, etc. So that's why calculus is important, no? Now, this is what I was telling you. This thing, we will see a little bit of differential equations. Differential equations, as the name says, is an equation describing the variation of two variables, y and x in this case. And of course, all the other terms can depend on y or x or be constants. There are ways to solve these equations. I will only show the most standard cases because differential equations is a difficult subject. There are differential equations that cannot be solved. Now, if you learn these concepts, subsequently, you don't need to calculate this by hand. You can use a software. And that will be one of the lessons, how to use the software for graph or integrating for finding derivatives or something. But I always think that learning the concepts is very important because if you just go and make a shortcut, which is a bad custom nowadays, many people want to learn quickly and make shortcuts. This is how you forget that the next day. I mean, the reason why somebody doesn't forget things is because that person doesn't make shortcuts. That person really studied the concepts slowly. You look slow initially. People will call you, you're too slow. No, it doesn't matter. Take your time, try to understand, because in the long term, you will remember. And those guys who were fast, they will forget. That's the payoff. Stephen Hawking, who was considered the smartest guy in the world a few decades ago, he was called slow learning. Actually, he is a guy who read each page slowly because he wanted to be sure to understand. He wanted to be sure to learn the concepts very well. And that's the way of not having to come back again to revise that, no? Especially for his condition that he has a special condition. Okay, now let's go to, I will close this part. I will go to the introduction of derivatives. Close this. Derivatives. I need to share the right window. Okay, here. Derivative, as I mentioned before, it measures the change of one variable with respect to the other. Remember, when you collect data, you are correlating two variables. You are trying to correlate variables. But sometimes you want to explore how much this variable change when I change the other. If I change x to another, for example, from 5 to 5.7, what is the change of y? It changed little, it changed a lot, it changed in the same way. What is the change? And that change is measured by derivatives. So when you take any function, let's do this. Any function, I will write one function here. Let's put this, y equal x squared. This is a function which runs like this. X, y. Remember that in your thesis, of course, when you plot data or so, you have to specify the units used here. And remember, the units have to be consistent. Remember the dimensional analysis. So here, sometimes you want to know if I change, let's put 1, 2, 3. If I change from 2 to 3, delta x is 1, this change. When I change this, sometimes I want to know how much is the equivalent change in y, this. Okay? And this is measured by derivatives. And if I go very, very small here to a neighborhood, this, any function, becomes a straight line. Let's say if I go here, I cut this portion and I separate, it becomes a triangle like this. Such that the triangle you see in the screen here, this one. And then you can measure the change in x and the change in y differentially. And this is how the concept of derivative was born. Because you assume that you're analyzing just a neighborhood, a small point, or a neighborhood of the function. And that allows you to calculate instantaneous rate of changes. So you are calculating the instantaneous rate of change of one variable with respect to the other. Basic concepts like velocity, acceleration, and others, rate of consumption, rate of sellings. For example, sometimes you want to sell chocolates, a store selling chocolates. You saw one store, they sold 1,000 chocolates in 1 month. The other store sold 1,000 chocolates in 15 days. They sold the same amount of chocolates, but one store sold it in half of the time. So the rate of sellings of that shop is higher. Okay? And that's measured with derivatives, the speed of selling. So, I mean, the concept of velocity, acceleration, also are not exclusive from physics. They are, because some people wonder, how this guy being physicist can do business. Because I wrote some papers in finance because the concepts are the same, man. That's the response. I mean, the mathematics are the same everywhere. The calculus is the same everywhere. The tools you use are the same in all the subjects. Mathematics is universal language. You just change the variables and it's the same. Then that's how a physicist, a mathematician, or whoever you wish, can do any field he wishes. Okay, he can work any field he wishes. Not very arrogant, but physicists and mathematicians can work any research they wish. It's a matter if they want or not. In most of the cases, they don't want work. There are cases they are flexible. So let's go in this way. So the point is that if you know math, if you know a little bit of quantitative analysis, that gives you weapons. It's like getting weapons for a battle, for a war. Your war is the PhD. You want to get the PhD, okay? And you are lucky. A good relationship with the supervisor is important, no? Because well, I know cases where the student-supervisor relationship was not good, and still the guy could graduate. Those cases are exceptional. But don't try. It's not. It's not a good idea. You will not sleep well. Okay. Anyway, these are just concepts. This is what I was telling to you. You want to know what is the change of one variable when you change the other. One is the independent variable, the other is the dependent variable. I will not ask you to evaluate this in this way, but here is where we will start with the rules of derivatives. When you have a function like x squared, which is this one here on the board, and I want to calculate the derivative of y with respect to x, this is 2x. 2x. How do you calculate? There is a universal rule for that. The derivative of a function with respect to a variable, when that function is let's put the function is a polynomial. Let's put like this with a constant. Then it's simply, well, let's delete the constant. It's irrelevant. The derivative of this is n x to the n minus 1. You can notice that this n is the number here. If this number is 2, naturally, this 2 goes down here. And then you have to discount here 1. 2 minus 1 is 1. For x to the 1 is like the same as x. No? X to the 1 is x. Then, this is a basic example. So what is 2x here? 2x is measuring me the instantaneous rate of change of x with respect to y. It also measures the instantaneous slope. For example, if I evaluate this function here in x equal 3 here, let's put this in x equal 3, then you will take 6. 2 times 3 is 6. What does it mean? It means that the slope of the tangent line here, if I put a tangent line to this, at this point, I'll put like this. This tangent line has a slope equal to 6. And then I can construct the equation of this straight line is 6x plus a cut. Because this is the slope, x is a straight line, tangent to this curve in this point. That's what the derivative measure. Okay? These things will be explained here. I will share these notes later, subsequently, and you have also the video. I will not ask you to evaluate derivatives in this form. This is the rigorous way to do it. But for example, if you want to evaluate the derivative of x to the cube, let's do it here. Okay. Let me delete this here. Let's delete this. Let's delete this. The function is x to the cube. And I want to calculate the derivative. 3x squared. Because this 3 goes down here, and then I have to discount 3 minus 1 is 2. Which is actually what these guys obtain here, 3x squared. And what does it mean? If I plot this function, cubic, the variation of x with respect to y in any point is measured by this quantity. This quantity also, when I evaluate a single point in any x, measure the slope of the tangent line at that point. Let's give a more formal example. Who has driving? You are driving a car, no? You drive a car? Car. Let's assume you drive 50 kilometers per hour. Constant. Constant. Then you have a velocity. This is how you define velocity. Derivative in position with respect to time. Is the change with respect to time of the position. And if it's constant, if this is constant, then it will be only the opposite. X and T should be here. It will be like this. A straight line. Now, what happens if it's not constant? If this gives you 3x plus 1, for example. So that means that the velocity is not constant. The velocity will change point to point. For different x, you will have a different velocity. That's what it means. Now translate that to your field. Array of ceilings. Let's put like this. Ceilings. Ceilings. I will represent with S. Let's assume that salines, you have a function of salines in time, behaving like this: constant A, t time squared plus a linear contribution plus some constant C. This is your curve of salines in time. Now I want to calculate the rate of salines. Rate of salines. Instantaneous rate of salines. This is my instantaneous rate of salines. This 2 goes down, decrease 1 here, derivative of a linear function, because there is a 1 here, okay? This 1 goes down, 1 minus 1 is 0, any number to the 0 is 1. So it will not appear here. And then you can calculate the instantaneous rate of salines at any time, at t equals 0, or 1, or 2, or 3, in any units you decided to analyze, because time could be in seconds, in hours, in months, in days, in years. Okay? It's more or less like that. Okay, later we will practice a little bit and you will see how easy is it. Now let's go to other notes. Let's go to derivative rules. I will close this one. Derivative rules. Later, I will teach you, especially those who are not familiar with mathematics, you will learn. I will give you a powerful tool, which is a free online resource, which allows you to calculate derivatives, integration, and so on without, they do it for you, basically. But what I'm teaching here, I need to teach the concept, no? So for you to understand, globally speaking, you will understand. There are rules for derivatives for different functions. For example, the derivative of a constant is 0. It means the derivative of 1, 2, 3, 4, 5, any number, the derivative is 0. The derivative of x is 1, ax is a. This is what we have been doing. When you have root square, when you have root square, for example, root square of x, this is the function. Derivative of the function with respect to x is the derivative with respect to x to the 1/2. Because root square is like the exponent 1/2, no? So this will give you 1/2 x to the minus to the 1/2 in the denominator. So it means this. And how do you know that? Because 1/2 minus 1 is minus 1/2. But when you have exponent negative, you have to put it in the denominator. So that's why you obtain this rule. Anyway, these are just rules. I will share with you the rules. The derivative of sine is cosine, the derivative of cosine is minus sine. And when you integrate, it's the opposite. You go from here to the left. Integration. There are some rules for the power. Well, this is what we have been doing. This is normal. When the derivative of the sum of two functions is the derivative of the functions, this is the same. The product rule is the derivative of the product of two functions is the derivative of the first times the second plus the derivative of the second times the first. I will give you an example. two functions, products of two functions. Imagine I have this x squared multiplied cosine of x. You say, I will never see this function in my life. No, it happens. Sometimes, even in economy, these kind of functions appear. Then I want to calculate derivative. Then it will be derivative of this multiplied by this plus the derivative of the second function, which is minus sine, multiply the first. These product rules, there are examples here. Look at this example. Let me see. Do you understand this example? For example, the derivative of x to the cube. Look at this. The 3 goes down. 3 minus 1, 2. It's clear, no? And what does it measure? This quantity measures what? I have said many times here. What does it measure? Guys, participation is one of the greats. Yeah. Remember? This measure the rate of change of x or y or let's say y with respect to x. Well, y is the function at the end. And this also measures the slope because the slope also measures the rate of change. It's the same. The instantaneous slope. So well, these rules, I will show you something interesting because obviously sometimes you want to save time. Then I understand you a little bit. I will show you right now an advance of the free online resource. Let me, I have to log in, sign in. I hope I remember the password. Whenever there's oscillation, of course, you will see sine or cosine, and that's related to complex numbers. Well, we will not see complex numbers or so. Yeah. Or so you don't use your the calculator, right? Let me see if this thing is sharing what it's supposed to share. Yeah. Okay, I will open a new notebook here. This is a popular software. It's called Mathematica. Many physicists use it, many scientists, etc., especially when they have to do complex calculations. And it's very easy because I can go here and search, and I put derivative. Derivative. Go here, and it tells me how to evaluate the derivative of a function, for example. Well, this notation is better. I like this more, for example. I copy here, I paste here, and I can, for example, let's put here 3x squared. 3x, I think a square should be like this. Then I go to evaluate cells. 6x. This is the derivative of 3x squared. Now what happens if I multiply this by, I will multiply by cosine. I think cosine should be like this, x. And I want to evaluate this derivative. Derivative of the first is 6x times cosine, plus derivative of the second is minus sine times the first. This is what I just did in the board. This is the result. So when you have more complex derivatives, you use this. But in most of the cases, the derivatives are very simple, then you don't need to use this. But of course, somebody like me don't need to use it. But let's say if your background is not precisely quantitative and you don't know so much calculus and you want to be sure, then it's like that. And you can simplify if you want, but I don't know how. Okay, if you simplify the group, this result is the same result as this, etc., etc., etc. And with integration, you can do the same. Integration is exactly the same. Great. Then now, let's go to important concepts related to derivative because now you know how to calculate derivatives. Because in the worst scenario, you will use the software, Wolfram Cloud. Free online resource. You can create a free account actually. Here, you go here. I will show you. Actually, you can create now. You go here for the future class when we see software. You go here. Google. Let me see the sharing. Yeah. Google. And then you put here Wolfram Cloud. Why I use Wolfram Cloud? Because I don't want to download the software. If you download the software, you have to pay license. I don't want to pay license. That's it. I am a miserable person. I don't want to pay anything. Not even for a research visit I pay. So it's a way to say that it's better to save money, no? Then let's go here. Okay. Because I have the open account already. But let me log out. If I log out, where I am here, log out, sign out, I mean. I will go again. Then it will ask you, sign in is for those who have account already. Sign up by free, for free. You can create your account and it's free. So it's not true that you have to spend a lot of money using software or downloading software or whatever. Let's be honest, in most of the research you do, the amount of quantitative, the analysis you do is probably minimal in some cases. In other cases, a little bit more. So you will not need a supercomputer for that. And I think a free online resource will be enough for that. Then, of course, this will help you to save money and so on. So now, this is the software we will use in one class. Everybody will have to bring laptop that day. I think I can see that everybody has a laptop here, so it's okay. It's quite nice that you have. Let's go to basic concepts of calculus. Now that we know how to calculate derivatives, not yet integrals, let's go here. In calculus, it's very important. It's very, very important to locate what people call stationary points or critical points because they measure something. They can tell you in which point you have the maximum sellings, the higher sellings, or in which moment of the year, in which month or so, you sold the most, or in which month you got broken, what happened, etc. It can give you details about what's happening with the dynamic of your system. In biological systems, could tell you in which moment an outbreak happens or why some species are getting extinguished, are disappearing because the rate of the reproduction is smaller, etc. Then must be something happening. And part of the research is to find the variables affecting the reproduction of a species and finding those critical points. Because those critical points mark something. I will tell you one critical point. When an asteroid fell in Yucatan, Mexico, 65 million years ago, and the dinosaurs got extinguished. You know that. You know that story, no? That was a critical point in the air, no? So obviously, you analyze the dynamic of reproduction of the species, the reptiles, and of course, that was convenient for the mammals, especially us, because that's why we are dominant now. If the dinosaurs don't get extinguished, human race maybe it would not exist, or we would not be dominant. Other species would dominate. Could be a smart T-Rex or something like that. Or maybe not that smart after all. Anyway, those critical points are represented by maximum and minimum. But since they are located at a specific point, we call them local maximums and local minimum. Saddle point is a point of inflection. It's a point of change of concavity. What does it mean? That means that when you have a maximum, what happens? Your function goes from a positive slope to a negative slope. It changes from positive to negative. So the derivative of this function here is smaller than zero. If you evaluate the derivative here, it's smaller than zero because it's measuring a slope which is changing from positive to negative. If you evaluate the derivative in a minimum, it will give you positive because it's measuring a slope which is changing from negative to positive. Remember, positive slope is positive correlation. Negative slope is negative correlation. We saw it before. And the saddle point is a point where the slope was negative and suddenly it tried to change, but it doesn't change. It continues negative. So it doesn't develop these stable points here. So we call this saddle point. They have some characteristic. The derivative in this point, and this point, and this point is zero. The derivative is zero. Sorry, I say smaller than zero. No, it's the second derivative, which is smaller than zero. I will correct this in a moment. The derivative in these points, in this point, in this point, and this point is zero. The second derivative at this point is negative. The second derivative at this point is positive. And the second derivative in the saddle point is zero again. So there are ways to know, because I say wrong initially. No, I say derivative smaller than zero. No, it's the second derivative. So there are ways to know in which moment your function becomes maximum, in which moments it becomes minimum. So you can know when is the maximum sellings or maximum views of YouTube or whatever. In which moment is the minimal views on YouTube or minimal sellings or minimal reproduction of a species or some inflection point in the history. In the case of Priscilla, for example, you are not Priscilla. What's your name? Huh? George. Joyce, sorry. Joyce. So Joyce, who worked with Priscilla, for example, she will not see so much these kind of things, but still, if you are studying some kind of history, there might be some patterns which you can plot, and still you can analyze some critical points in the history, let's say. There are some events which change the history also, and that can be quantified, actually. Can be. Your business. Okay, great.
That's a reflection, that will be changed to the negative, right?
Yeah, exactly. The second derivative. No, I mean, the second is important because the second derivative tells you whether it's maximum or minimum. The first derivative just tells you that the slope at this point is 0 because the slope is horizontal, no? The tangent line at this point is horizontal. So those are lines with 0 slope, a slope 0. That's why the derivative is 0 there. However, the second derivative here is different in sign to the second derivative here. In this case, it's negative, and in this case, it's positive. And in this case, it's 0. Then, of course, the second derivative is important for distinguishing whether it's maximum, minimum, or inflection point, saddle point. But the first derivative doesn't distinguish. The first derivative just tells you in these points, the slope is 0, so those are either maximum or minimum or saddle points. But doesn't tell you what is what.
The first one is correct. Is it like that?
The purpose of what?
I understand it because the apply for the business model. So my purpose is to want to find out where is the highest self part and the lowest, right?
Yeah,
Is that sure?
sure. Yeah. Or analysis of revenue or so.
Negative is because the low, the maximum will become a negative, right? That's not you tell me that.
No, what is negative is the second derivative. But it doesn't mean that the sellings are negative. Yeah, it's the second. Because the second derivative gives you the rate of change of the slope. So if the rate of change of the slope is negative, of course it's a maximum. Let's put it this way. It's like going in a car. I will paint that here on the board, and you will decide better. I have this function here. X, Y. Well, let's put it sellings in time.
Yes.
Which is, let's assume that you have a chaotic plot. Chaotic. This is a crazy function. Then if I calculate the S dt and I set equal to 0, the solution of this will give me this point, 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 this, all the points, and this also. All those points will be defined. Well, this is almost a small maximum. All these points are given by this condition, but they can be maximum or minimum. There is no distinction or saddle points. Now, when I evaluate the second derivative, if it's smaller than 0, it means you are changing from positive slope to negative slope. That's a maximum.
Because we're putting as a less than 0.
Smaller than 0. No, you calculate. You have to calculate and replace. This is imposed and you solve. Let's assume that you obtain here 3 days. Let's assume the time is in days. Then in 3 days, you got a maximum of sellings. Then, of course, this is solving from here. You obtain up in the time 3 days. Then after you take the function and you calculate the second derivative. And you have to evaluate that derivative in 3 days. When you replace these 3 days inside the solution of this, you obtain a number. That number could be positive, negative, or it could be 0 also. Well, you have to replace the 3 here. Well, this is imposed. We will do a problem later. We will solve some problems for you to understand. Well, let's say the idea is I have a function. Let's say that s is t squared plus 3t cubed plus 4. These are my cells in time. Then I want to impose this condition. Then I have to evaluate the derivative. 2t plus 6t squared equals 0. Then I solve this. 2t plus 6t equals 0. So there are two solutions for this. One is 0 time, and the other, well, I think it's not so clear. Let me delete everything first. It's not so, you will understand what it is. Let me delete everything for you to get it. Let's write the function again for it to make it clear. Let's put an arbitrary function of time. 3t to the cube plus 2t squared plus 1. This is my cellings in time. My time is in days. I want to find the critical points. What do I do? Well, it's the same. Then I have to factorize, no? 9t plus 4 equals 0. There are two solutions. One is in 0. The other is when 9t equals 0. But in this case, because I put a wrong sign, well, let's put minus here for the example to be better. Then this will be minus here. This will be minus here. And this will be minus here. Yeah, because I just invented the function. I have to do something consistent. Then for the time to be positive, no? Then the time is 4/9 of a day. It's not even 1 day. 4/9 of a day. It's just an example. Or it could be other units, a year. It could be in years, the time. So this is telling me that time 0 and time 4/9, I have critical points. I have either maximum or minimum or saddle point, but it doesn't tell me anything else. For knowing whether those points are maximum or minimum, I have to evaluate the second derivative of this function. Then I come here, second derivative of this will be 18t minus 4, right? And I have to evaluate that in t equals 0 and in t equal 4 divided 9, right? So let's evaluate in t equals 0. If I replace 0 here, I obtain minus 4. So it's negative. The second derivative is negative. So in t equals 0, I have a maximum. There is a maximum. That function is maximum. And I don't have to plot the function for knowing that. I already know that that point will be a maximum. Now, if I replace 4 divided 9, 18 with 4 divided 9, this will be 2, is 8, minus 4 is 4, is positive. So if it's positive, it's a minimum. So this is how you know whether it's maximum, minimum, or saddle point. It's the second derivative. Will tell you that. When the second derivative gives you 0, it doesn't mean it's saddle point. It could be something else. The criteria doesn't decide. And there are cases where this criteria fail. I will give you an example where that criteria fails. There is a function, and this is a typical example. In mathematics, this is a typical example. Don't worry, this and the tomorrow session will be the most mathematical sessions after we go back to the statistics and software and whatever. But this function. This function This is a minimum, no? Here, I come. But the derivative here is not defined. If you calculate the derivative here, it will give you an infinity, it's undefined. This function is absolute value of x, which is positive on the right-hand side, negative on the left-hand side. This function doesn't have a derivative defined in zero. It has the derivative defined for x positive, for x negative, but not for zero. So there are cases where you cannot apply this criteria, but in most of the cases, most of the known cases, you can apply it. You can apply it. And where there are oscillations, for example, a system with oscillation is cosine or sine, for example. Let's assume you have a system oscillating cells or whatever. You have the time here, you have the settings here, and suddenly your settings are behaving like this. Let's put like this. This is a sinusoidal behavior. These behaviors are typical of cosine or sine of p. And the derivative of cosine minus sine, the derivative of sine is cosine. These two functions are displaced with respect to each other 90 degrees. They are shifted 90 degrees. If you shift this 90 degrees, you obtain the other. You displace that curve. So these functions appear in probably theories, dealing with some stocks or whatever. You can find this kind of function. And of course, in the nature, it appears everywhere. But I will not emphasize so much on that because anyway, you have the software which help you to evaluate things. So now we know how to calculate maximum and minimum. And then there are local maximums, local minimum, but also there are total maximum. The total maximum between these two guys is which one? This is the maximum because this is larger than this. This is just a local maximum. And the minimum, of course, is this. There is only one minimum in this function. This example, I want you to work this example by yourself to demonstrate me that you can calculate maximum and minimum. And after this, we will go to some optimization problems. So please try to calculate with this function here. If this is a max, where are located the maximum or minimum for this function? This is the function, the plot. You can use a software if you want, but try. And whoever do it, bonus, big bonus, giant, monumental bonus. This finished the first part of the class. I will stop the sharing here. Start sharing.